Well, all right, I think we have done enough to sort of absorb what's going to come. Okay, so I'm going to talk a little bit about plant-wide control, the hierarchy of layers that you see in actual implementation on different plants. Okay, in that hierarchy you've got the regulatory layer, then you've got the supervisory layer, and then you've got the real-time optimization layer. I'm going to talk a little bit about all of these layers and what are the tasks that you want to do. Then I'm going to talk about structuring for tight active constraint control, because tight active constraint control is the key to economic plant-wide control. Okay. Then I'm going to develop a systematic procedure current version, which has been told to you formally, informally, in different ways, but hopefully will. And then there's a couple of case studies. I don't expect to cover more than the first 2 bullets today. Here is a simple chemical process. What is the one thing that distinguishes chemical processes from everything else? Actually, what is the one thing that complicates everything? Recycle, exactly. So you are recycling unused reactants back, you are recycling energy, whatever energy is released in the reaction you are using it to create boil up, for example, in a column, and so on and so forth. So there is material and energy recycle. I hope this is a controls course, right? If you have negative feedback, you can always screw up the tuning so that you get an unstable system, right? If you didn't have feedback, stability wouldn't be a problem for most systems. Okay, the moment you start putting in feedback, stability becomes an issue. Yes or no? You can always screw it up to make it unstable. Yeah. Okay, so when you have a feedback, you have stability issues. So feedback is a necessary but not sufficient condition for stability issues. Okay, so if you have an unstable system, guaranteed there is some kind of feedback that's happening. But if you have feedback that's happening, there is no guarantee that the system would be unstable. You know, it's a necessary but not sufficient kind of condition. So in chemical processes, because you got material recycle, material feedback, and energy recycle, energy feedback, you have the potential for instability. Okay, that instability is what we are supposed to manage. So chemical processes are highly integrated with material and energy recycle, and this creates issues for regulation. Okay, so well, we need to run our plant 24 hours a day in a safe, stable and economic manner, and economics implies you want to produce whatever is being asked, determined by market demand supply considerations. You want to produce the product of the right quality but not too pure, because then you are there is a product giveaway there. Also you want to meet effluent specs, greenhouse gas emissions, and discharge, blah blah blah. All these specs are by regulation required to be controlled. You can't violate them, and so on and so forth, right? So this is what governs economics. Now we want to operate the plant to meet all these objectives: safety, stability and economic objectives all the time. And this we must do when the production objective itself can change. What do I mean by that? Tomorrow I may need to make a different product mix. Today I want to produce more gasoline, less diesel. Tomorrow I may want to produce more diesel, less gasoline and more of heating oil, because winter season is coming and heating oil demand is going to go up, and so on and so forth, right? The product mix can change. How much I need to produce can also change. Let's say there is a war and some chemical is in great demand. Well, then you need to jack up production to 100%, produce as much as you can, and so on and so forth. So it's all determined by economics. Okay, and of course there are always disturbances. What are the disturbances? Ambient conditions are always changing. Raw material quality is not fixed. Sensors are noisy, with bias, and never. If the sensors are good for one thing, they tell you if things are changing, if the temperature is going up or down, that you can rely on. But if you say temperature, sensor is saying 100 degrees Celsius and by God it is 100 degrees Celsius, no, it may be 101, it may be 99, you never know, right? So sensors are good for detecting changes but not absolute values. Okay, so sensors, equipment characteristics, your catalyst is fouling up, your catalyst is losing activity, your heat exchangers are fouling up, things are accumulating in a column, and therefore it is getting closer and closer to its flooding limit, because there is some impurity accumulating inside the column, surface tension is changing, etc., etc., etc. Equipment is always changing its characteristics. Okay. I didn't add to this, but there is also economic disturbances. War in Libya, crude price shoots up, energy is much more expensive. Now that Libya is settling down, crude is back down. There is economic volatility, right? So there is also economic disturbances. Yeah, somebody passes a regulation today, this was junk, but tomorrow this may be very useful, because there is a regulation that has been passed, that material cannot be used to add, cannot be blended in gasoline. Well, this can be. That used to give me much better octane enhancing, that used to enhance the octane number much better. This does, but not as much better. But now that the regulation has banned that, well, this is hot. These things happen. Okay, these are also very large disturbances. Okay, so there are always disturbances, and I need to operate my process regardless of these disturbances in a safe, stable and economic manner. Okay, how do you do it? So you've got your control valves in the plant, that's the bottom, you see a bunch of valves. First task is, I need to stabilize my process. What are the things that have potential for instability? Things related to recycle. Yeah, and what are those things? We talked about the snowball effect. Yeah, that's got to do with recycle. You also have to make sure that the heat released in the reactor is removed effectively. It should not happen that it gets recycled in a manner that the temperature inside the energy recycle loop just keeps on going up, just like material inside the flows inside a material recycle loop keeps on going up, right? Those kinds of things should not happen. So these are stabilization issues. I need to make sure that my process inventories are managed properly. What are the inventories that we are talking about? Liquid inventory, gas or vapor inventory, energy inventory. Okay, that's what the stabilization layer is supposed to do. So the regulatory layer adjusts valves to make sure these issues don't bother you. These issues are taken care of. Now once these issues are taken care of, there are set points in the regulatory layer. How much should my recycle flow rate be? What should my reactor operating temperature be? Temperature is being removed by adjusting cooling duty, that stabilizes the reactor, but I can always adjust the reactor temperature. It may be 200 degrees Celsius, it may be 205 degrees Celsius, it may be 195 degrees Celsius. How much should it be? So there are all these set points. These set points need to be managed in a manner which is quote unquote economically sound. How do you do that? Well, that's what you do by the supervisory layer. The supervisory layer is adjusting set points in the regulatory layer. Now because disturbances are there to the process, equipment characteristics slowly but surely change. You also have a real-time optimization. You may have a real-time optimization layer. Okay, so this is which adjusts set points in the supervisory layer. Okay, this is the typical hierarchy that is implemented in plants. You may do away with this by controlling things that are economically sound regardless of disturbances. I may even be able to do away with this, and then what I have is the simplest possible implementation that takes care of stability and economics in a single layer. Okay, the case studies are sort of geared towards showing you these aspects. Okay, now regulatory layer, well, you got interconnected units, there is material energy recycle. Manipulating a process stream necessarily disturbs the connected units, and because you got recycle, the variability propagates through the entire plant, right? It's not that I do something here and only this gets disturbed, everything that's connected to it gets disturbed, and since you got recycle, essentially the whole damn plant gets disturbed. Yes or no? Okay, so therefore the regulatory layer has got two main, basically inventory management, energy management, that's essentially got to do with stabilization. Also throughput manipulation, that's because at least one set point in the regulatory layer must be used to decide how much is flowing through the system. That's your throughput manipulator. What's your throughput? What's your process throughput? Okay, so these three aspects are the domain of the regulatory layer. Now I want to show you that there are different possible control structures even for this simple plant. What do you have here? An isomerization reactor, A goes to B, exothermic, reaction heat is being removed by cooling water, B is heavier than A, so the column recycles A at up the top and B is taken down the bottom, and the stripping section essentially makes sure that A doesn't contaminate B. Yeah, this is your process. By the way, what's the degrees of freedom of this process? Steady state operating degrees of freedom of this process. One for the steady state operating degrees of freedom. It's a very specific question with a very specific answer. What is the answer? 4. Including or excluding the throughput? Excluding the throughput. Including the throughput? 5. Okay. So there's 5 degrees of freedom including the throughput. Okay. So let's say I set the throughput at the feed. Okay. Then I have to control the reactor temperature, control the reactor level. I do it this way. Then I have to manage the inventories on the column. Then what I do is I keep the reflux in ratio with the feed so that too much B doesn't go up the top, and I maintain a stripping section tray temperature by adjusting the boil up so that A doesn't contaminate B. Yeah. Look at the number of set points that the operator has in his hands. One is the throughput, 1, 2, 3, 4. 4 set points that he can play with to get the kind of operation that he wants. Yeah. Is this the only possible option? No, there's other options. I can have an on-demand control structure, and now what happens is the reboiler level will get controlled using the column feed, the reactor level gets controlled using the fresh A, the rest of the control system remains the same. What are the set points? Well, these are the set points that the operator now plays to get the kind of operation that he wants. Yes or no? Is this the only option? No. I could have my throughput manipulator over here, and then this level controller is in the reverse direction of flow, downstream, the rest of it is the same. Again 5 set points, excluding the throughput 4 set points that the operator can play with. Yeah. There is another possibility. Again 4 set points. Yeah. Well, here's another possibility. You name it, there are always possibilities, right? Now level control is this way. Level control before the throughput manipulator is in the reverse direction of flow, beyond the throughput manipulator is in the direction of process flow, blah blah blah, and again the operator has got 4 set points that he can play with. By the way, the reactor level controller is a set point that adjusts the steady state, because by adjusting the reactor level I am adjusting the residence time, and that affects the conversion and therefore the steady state. Yes or no? Okay. What's the point? The point is location of the throughput manipulator is a key decision in deciding the orientation of your level loops, your inventory management loops. Yeah. There are several alternative reasonable plant-wide control structures that will give you stable operation, which will make sure the energy and what's the other one? Material inventories are regulated. Things don't build up. Okay. So there are several reasonable control structures that will give you stable operation. There is no issue, right? Which one is the best? That's the question. Which one is the best? Okay. अभी पाँच या 6 दिखाया ना. I showed you 4 or 5. Which one should I implement? That's the question.
Depends on your needs.
Precisely, what are my needs?
Throughput, quality.
So that's what we are going to address. That's what we have already addressed. We're going to address it again in a slightly more reasonable way. Is there a systematic way of designing the best control structure? Okay, that's the question. Now what does best mean? You need to know what the hell is best. The bottom line. So for continuous chemical processes, the bottom line may mean I want to maximize production rate. Give me as much production as you can give, because we have the patent to the process. Only we have the license to this process. Nobody else can use this process. there is sufficient demand, no matter how much you produce, you can sell it and command a premium, right? So how do I maximize my profit? Maximize production. It so happens that what we are doing now, there are n number of competitors. I shouldn't end up in a situation where I produce so much, that guy also produces so much, that guy also produces so much, and then there's so much supply in the damn market that the prices fall, and then all of us go out of business, right? So what do we do then? Then we move as a cartel. So that will not, so there is a demand supply analysis that some business group will do, and then they'll say you need to produce so much, which will be less than max. Okay. So for a given throughput, then what you're supposed to do is run your process for example, maximizing its yield to desired product, for example, minimizing the energy consumed per kg product produced. That's the most energy efficient operation, or a combination of the production, yield and energy, which would be, for example, in an operating profit kind of thing. Revenue made by sales of product minus money spent on buying raw material minus money spent on energy plus electricity plus whatever, right? So you could be, any of these could be an economic criterion. A lot of thought needs to be given on what makes a good economic criterion, but that's a separate thing. Okay. Of course, when you are maximizing or minimizing one of these criterion, you will always have there will always be process constraints that cannot be violated. You are not free to change the reactor temperature all over the place. You can only change it in a certain band. You cannot change the boil up in a column all over the place. You can only change it in a band such that the column doesn't get flooded. You cannot change the flows all over the place. There are limits. The pump can only deliver so much flow, and so on and so forth, right? So there are always process constraints. You want to optimize your objective, economic objective, subject to process constraints not getting violated. Yeah. Okay. So when you want to run your process for good economics, you want to optimize the available steady state operating degrees of freedoms for an economic criterion, which could be whatever, subject to process constraints. Product quality is also a process constraint. You cannot make a shitty product which cannot sell in the market. Effluent discharge is also a process constraint. You just cannot put in the stack everything. The regulator is going to come and say shut it down, or at least demand an economic penalty, right? There is an economic penalty associated with it. Safety constraints. You cannot run the process such that your operation ever gets into those flammable regions, right? So there are always these constraints that need to be respected. Okay. So you optimize the available degrees of freedom subject to process constraints, and your operation mode is actually two operating modes. One is given throughput, where the business group is telling me demand supply situation is like this, you produce so much for the next 1 month. Okay. Alternatively, you could also have your business group telling us that, oh, maximize throughput, give me all that you can give, right, and so on and so forth. Okay. Now if you look at your plant, it is designed for a certain capacity, and depending on the economic scenario that is existing, you may be required to operate the plant at a low throughput, at an intermediate throughput, at a high throughput, or maybe even at maximum achievable plant capacity. Okay. At each of these throughputs, multiple process constraints are active, and as you are going from low to high throughput, more and more constraints become active. In the worst case, what you can have is that the maximum number of constraints that are active is equal to the total number of steady state degrees of freedom that you have. Okay, so at maximum throughput, the maximum number of constraints that you can have active will be less than or equal to your total number of steady state degrees of freedom. Okay, so if you got 10 steady state degrees of freedom, you could at max throughput at best or at worst have 10 active constraints, where you are using all those 10 steady state degrees of freedom to drive as many, that is 10 constraints active. Yeah. Alright. So at a given throughput, economically optimal operation corresponds to process operation at the limit of all active constraints, and if some of the some of the steady state degrees of freedom are unconstrained, that means they have not been used to drive a constraint active. So let us say your process degrees of freedom is 10, at max throughput 8 constraints are active, that means you got 2 unconstrained steady state degrees of freedom. Those unconstrained degrees of freedom, steady state degrees of freedom, correspond to trying to control something, a variable which is quote unquote economically sound. Okay, so these are the two things that you need to do: drive the process to the limit, whatever constraints are active, and manage the unconstrained degrees of freedom in an economically sound manner. These are the two things that you need to do. I think we agree on this. Now, you get back off due to transients in hard constraints. What are hard constraints? Hard constraints are constraints that can never be violated, where hitting that limit is not allowed. For example, a constraint should not be flooded. So flooding imposes a hard constraint on for example the boil up. The boil up cannot exceed this, because else the column will flood. If the column floods, then you have to, well, not really shut down, then you have to do things that you don't really want to do. Okay, so these constraints would be labeled as hard constraints. On the other hand, you could have soft constraints. What are soft constraints? Where for small durations, deviations beyond the limit are allowed. So for example, you may say catalyst temperature should not exceed 400 degrees Celsius, but if for a small duration of time it goes to 402, 403 and comes back, that's okay. Yeah, similarly product impurity also, you could have a small duration of operation where the product is slightly more impure than it should be, but then you can always compensate for it by producing product that is over pure, and when you mix in a tank, the tank purity is okay, right? So these types of constraints are soft constraints. There are hard constraints. Valve gets saturated, that's a hard constraint. 100% means 100%, fully open valve or fully closed valve, right? That's a hard constraint. Okay, so depending on the structure that you have implemented, depending on the control system you have implemented, there will be transients due to disturbances, because disturbances are always there. And now let us say I am looking at a variable that is supposed to be at its constraint, and I look at its transients. So if you look at those transients, go to the figure, you see this transient. Now you are not allowed to exceed that max limit, and the worst case transients looks the way it does, and therefore your average operation is backed off from the max limit. Yeah, you could have a structure in which, or a control system in which, the transient in the constrained variable is less severe. If it is less severe, then you get a less severe transient, and therefore your average operation is closer to the max limit. You could also have a structure where you are able to do this, where your back off is negligible, so that you are operating at the constraint limit. Okay, it all depends on how you have oriented or designed your control structure, and that we will see later. So between these three, the most desirable would be the third one. Okay, all right.
Sir, any example of the third one?
Yeah, we'll get an example. No worry. Now let us say you have one of the scenarios and you have some back off. You see, there are 10 active constraints. Which active constraint gives you the maximum penalty due to a back off? Okay, that active constraint you would like to control the tightest, and usually the economic loss or the economic penalty associated due to a back off is proportional to it. It's proportional is equal to a gain times the back off, the simplest linear relationship. Okay, and this gain Ki is actually the sensitivity, or if you do it from optimizing the Lagrange multipliers, the Lagrange multiplier is the economic sensitivity of the objective function to a back off. Okay, so constraints that are active, that have large Ki, that have large Lagrange multipliers, or that have a large economic penalty associated due to a back off, those need to be controlled really tight, so that the back off is as small as can be, so that your economic penalty is as small as can be. So therefore what that means is that the control structure should be structured to mitigate transients in active constraints with large economic penalty, that is large Ki. I indexes the constraints that are active. Yeah, that's clear? Okay. Now, how do we structure a control system so that you get less severe transients in constraints that are active, particularly less severe transients in economically important active constraints? Yeah, how do we structure? Now that's the next thing that I'm going to try and explain. Here is an heat exchanger. Here is a heat exchanger. Okay, you got a process stream going in and a process stream going out. Steam is being used to heat that heat exchanger, that process stream. Okay, now let us say I am running the process with the steam valve fixed. The steam valve position is fixed. I am not moving it. Okay, so the steam flow is essentially fixed, and therefore the temperature of the process, the outlet temperature of the process stream will show fluctuations because heat loss across the heat exchanger is changing, because nights are cold, days are warm. Yeah, there is rainfall, there is sunshine, no sunshine, etc., etc. Also the process stream that is coming in, its temperature is fluctuating, its flow rate is also fluctuating. Okay, therefore there are transients in the outlet temperature. So this is the situation when I am running the heat exchanger open loop. Steam valve is at a fixed position, so the steam flow is fixed, the outlet temperature is going all over the place. Yeah. Now I say, well, the variability in the temperature is not acceptable, because let us say this stream is going into a reactor or whatever. Okay, so this variability in the temperature is not acceptable. If this variability in the temperature is not acceptable, what I do is I put in a control loop that manipulates the steam to keep the temperature constant. Yeah. Then what is the situation that I get? Then what I get is the steam blows all over the place, and the transients in the temperature are much less severe. The variability in the temperature is much less. Yeah. So what is the control loop doing? The control loop is transforming variability from the controlled variable, which is the temperature, to the manipulated variable, which is the steam flow. Yeah. Okay. So therefore any control system can be looked at as an agent for transformation or management of process variability. Depending on what I am manipulating, I am transforming variability to whatever I am manipulating. Yeah. And therefore what I would like to do is structure my control system such that the variability is sent to where? Things that don't make a damn difference to the economics of the process. What are those things? I would like to transform variability to surge levels, because no matter how much the reflux drum level varies, as long as high alarm and low alarms are not being hit, it doesn't make a damn difference to my economics. Yes. Similarly, utilities. I am transforming the variability to utilities. Utilities are like steam and electricity and cooling water. Yeah. Those are also locations that are benign locations where I can transform variability. So I would like to structure my control system so that all the variability is taken in the levels and the utilities. That's what I'd like to do ideally. Yes or no? Do we agree on that? Okay, once we have agreed on that, now let's see how do we structure control systems. So here is a 3-unit in series process. We have seen this before n number of times. I set the throughput here. Level control then has to be this way in the direction of process flow. Unit 3 is starred, so it is the bottleneck unit. That means this unit cannot handle more than a certain amount of flow. There is a capacity constraint on unit 3. Okay. So if I want to operate this unit, and let us say maximum profit corresponds to maximum throughput, so then what would happen? You see what will happen is the throughput manipulator is the calmest place in the plant, so the flow there is fixed. Then due to disturbances to unit 1, the level controller does its own job, and therefore the flow to unit 2 shows some variability. Add on disturbances to unit 2, and therefore flow to unit 3 shows still larger variability, and the flow out from unit 3 shows much larger variability. Yes or no? Now if there is a capacity constraint on how much maximum flow that unit 3 can handle, I must choose my throughput manipulator set point such that that maximum constraint that is shown in red is never violated. And then this hashed area is lost production, this is back off, and this back off is causing economic loss. Lost production is lost profit that I can never recover. Yes or no? How do I get around this? Well, I say, well, if my throughput manipulator can be set here, then the bottleneck unit is, or the capacity constraint unit is my calmest location. That's where the flow is fixed, no variability. So therefore, in this situation, I have no or negligible production loss, because now my capacity constraint unit is operating at maximum throughput and I am taking variability away from the bottleneck. You see, look at the orientation of the level controllers. The level controllers or the inventory loops are oriented such that flow variability is being transformed away from the bottleneck unit or away from the capacity constraint unit. Yes or no? Yeah. So this way of managing inventory naturally transforms flow variability away from the capacity constraint unit, right? So one thing that comes out is you can always use your throughput manipulator close or at the bottleneck or capacity constraint unit. Yes or no? And then I will not lose production. But this you can do only for one constraint. Typically there are, at max throughput, if your degrees of freedom is 10, many a times you will find that there is only 1 or 2 degrees of freedom left. Sometimes even a single degree of freedom won't be left. I will show you an example today. Okay. So one constraint can be tightly controlled. What about the rest? Okay. We'll see how to manage that. Also, the other thing is, now what is the operator doing? He is looking at the capacity in the top case. He is looking at the capacity constraint in unit 3 and then adjusting his throughput manipulator set point. Yeah. In this case, in the bottom case, he is looking at the capacity constraint in unit 3 and then he is adjusting the throughput manipulator set point. Yeah. The loop, the top loop will be sluggish, slow. The bottom loop will be fast, tight control. Yes or no? Okay. So this essentially says that locate your throughput manipulator close to the economically important active constraint. Yes or no? Okay. Of course, yeah. Slow dynamics, loose control, higher back off or derating. Fast dynamics, tighter control, lower derating or back off. Yeah. So the key insight is, a plant-wide control system transforms variability through the plant, through the pairings. Yeah. We must structure the control system to transform variability away from the active constraints, particularly the economically dominant ones, the economically important ones. And not all constraints will be, the economic penalty for 1 or 2 or maximum 3 constraints will be large, the rest will not be that significant, right? Okay. So locate the throughput manipulator at or as close as possible to the economically dominant active constraint. Yeah. This naturally transforms variability away from the bottleneck or active constraint, the economically dominant active constraint, and also active constraint controller that you install will have faster dynamics and therefore tighter control. Yes or no? We agree on all this? Okay. If we agree on all this, then we go. Now we are ready to suggest some guidelines. Okay. If you want to minimize back off in active constraints, that means all active constraints should be tightly controlled. What do you mean by tight control? That means its manipulation handle should be close by. It shouldn't be that I am controlling the level here by doing something in Timbuktu, right? If I want to control the level of this unit, well, I better use a manipulation handle that's associated with this unit. Yeah. So to minimize active constraint, to minimize the back off in active constraints, all active constraints should be tightly controlled. What that means, but you note that as you are increasing the throughput, more and more constraints are becoming active. And let us say your plant, you want to operate your plant over a wide throughput range. It's like you want to drive your car over a wide speed range. Then if you know what constraints are going to become active, constraints can be of two types: input, output. What is input? Reboil steam to a distillation column. What is output? Composition of whatever is coming out of the distillation column. A controlled variable is typically an output, a manipulated variable is typically an input. Okay. So let us say your set of active constraints as you go from low to high throughputs, input 1 becomes active, input 2 becomes active, input 3 becomes active as you are increasing the throughput. This column reaches maximum boil up capacity, that column reaches maximum boil up capacity, that furnace reaches maximum heat duty, etc., etc. These are all input constraints, right? Now if you know that these constraints are going to become active, then whatever you are using to control these inputs with, whatever is being controlled using these inputs, you will lose control of that variable. So let us say, for example, a furnace heat duty hits maximum, and let us say I am controlling a temperature using the furnace heat duty. What that means is I lose temperature control once that furnace heat duty becomes active. Yes or no? Let us say I am controlling boil up, I am controlling a column tray temperature using boil up, and the column reaches flooding limit, so boil up reaches its max limit. So once that boil up reaches its max limit, I lose temperature control on the column. Yes or no? Okay. So what that means is, if there is an input constraint that becomes active, we are going to lose control of whatever it is being used to control. Yeah. So when I am structuring the control system, and I know that these constraints are going to become active, then what I need to do is control things that are non-critical. See, this input is going to become active at some throughput. If it is being used to control something important, well, then that the control of that important thing is going to get lost, and there are going to be consequences of that. So for example, let us say I am controlling the purity of a product using boil up, and that boil up becomes an active constraint. So whenever that boil up becomes active, I will lose product purity control, then I will be producing junk which I cannot sell. Well, then even though my plant is capable of giving me more throughput, just because I structured it such that I was using boil up to control product purity, and boil up became active much earlier than the maximum throughput limit, I am not able to reach my maximum throughput limit. Yes or no? Does this make sense or no? So what we are basically saying is, if you know what input constraints are going to become active as you are jacking up the throughput, use those constraints to control things that are not critical. Okay, product quality is, for example, critical. Reactor temperature control is, for example, critical. You cannot afford to lose temperature control of a reactor, because highly exothermic reactors are typically susceptible to runaway. Yeah, and so on and so forth. Okay. So the guideline is, use input constraints that become active only for controlling a variable whose control can be given up when the constraint limit is hit. That is, to control non-critical things. Okay, whose control when you lose doesn't make a big difference. The plant remains operable, plant remains safe, plant remains stable, and your product quality and effluent discharge, etc., is still maintained. You know, those critical things are still maintained. So what that means, obviously you cannot control these things using, right? You can control what are called self-optimizing controlled variables. What are self-optimizing controlled variables? There is a lot of theory that goes behind it, but basically a self-optimizing controlled variable is a variable which, when I control that variable, even though there are disturbances, for example large changes in throughput, okay, I operate the plant at a fixed set point. The set point for that variable is kept fixed. Large disturbance occurs, even though the set point is not changed. Usually what will happen is, if there is a large disturbance, optimality will require that this set point be different to be optimum at the disturbed state. But these self-optimizing variables are such that even with the disturbance, this set point remains near optimal. Do you see what I am saying? if I have a certain throughput, I have a certain optimum reactor operating temperature, let us say. Now let us say I want to jack up my throughput by 50%, that is a large disturbance. Okay. Do you expect that at that large throughput reactor optimum temperature would be the same as at the low throughput? Its set point would be different, right? Yeah. So what that means is, as the disturbance is occurring, you need to change the reactor operating temperature in order to remain optimal. Yes or no? Now self-optimizing variable is disturbance is here, disturbance is here, the optimal set point here and the optimal set point here is about the same. You understand? So I really don't need to change the set point. So a constant set point operating policy is near optimal. Does that make sense or no? So even though disturbance is occurring, large disturbances are occurring, by operating the plant at a constant set point for that variable, whatever that variable may be, I am having negligible loss, negligible economic loss regardless of occurrence of disturbances, large disturbances. So such variables are called self-optimizing variables. Does that make sense? Okay, so self-optimizing variables have got an economic consequence. Yeah. So if you can find a self-optimizing variable that gives you near optimal, by holding its set point constant, you get near optimal operation over a large throughput range. Those are good variables for your what? Those can be controlled using inputs that may become active, because when I lose control of that variable, I don't have a stability issue, I don't have a product purity issue, I don't have a effluent discharge issue, and I don't have a safety issue, right? The only issue I have is some economic penalty, that is okay. I don't lose critical things that will make the plant unoperable. The plant remains operable, right? So what is on the left should not be controlled, what is on the right may be controlled. So they call it self-optimizing CVs, but you can use your common sense and actually engineering common sense and figure out what needs to be controlled, right? Okay. Corollary to this is
what are green control variables?
Green CVs, effluent discharge. You know, you cannot pollute so much, you cannot release so much H2S, etc., etc. All right. Okay. A corollary to this is that active constraints can be of the input type, active constraints can also be of the output type. Okay. If an active constraint is of the output type, that means I need to control for my reactor, for example, at maximum temperature, allowed temperature, okay, at the constraining limit. I should not be using inputs that saturate to control an output constraint, yes or no? Because whenever that input will saturate, I will lose control of that output constraint, and that output constraint is economically important because you are trying to drive it to the maximum limit, yes or no? So a corollary to this is active output constraints should not be controlled using inputs that saturate or that become active, and also to get tight control you should use close by manipulation handles. You should not be controlling this by using a manipulation handle that is far off, because then the loop will be slow, you know, you will not be able to do much in terms of reducing the back off, yes or no? So these two guidelines are clear. Okay, we keep going. Handling unconstrained degrees of freedom, control economically sound CVs, self-optimizing CVs that ensure near optimum operation over large throughput range. Large throughput range is like a large disturbance. Regardless of the disturbance, your operation is near optimal. So for example, control the reactor selectivity to be 95%. So no matter whether your throughput is this or this, if you are ensuring 95% selectivity, that means you are not producing junk, too much junk, that means you are, if not optimal, near optimal, right? So this reactor selectivity or process yield may be deemed a self-optimizing controlled variable. Yeah. control reactor conversion to ensure near complete conversion of ethylene or propylene, okay, because ethylene propylene are expensive raw material. So if the conversion is near complete, then what does that mean? That means you are not discharging precious ethylene or propylene to the flare. That is also economically sound. Yeah. So reactor conversion or ethylene conversion or propylene conversion would be called a self-optimizing CV, etc., etc. Okay. So examples are process yield, reactor composition, excess ratio, conversion, right? And these variables are called self-optimizing CVs. Yes or no? Throughput manipulator selection. Use an economically important input constraint variable that becomes active as throughput manipulator. You can also sometimes use an output constraint that becomes active as a TPM. For example, reactor temperature could be a throughput manipulator. Limiting reactant concentration in a reactor could be a throughput manipulator, right? But usually what you will find is an input constraint is the last constraint to become active, and that last constraint to become active, because that is the last constraint that becomes active, that means if you reduce it, you are reducing the throughput. Yeah. So using that last constraint that becomes active, you can change the throughput from very low to very high without changing the throughput manipulator. Yes or no? I mean, again, maybe this time I can try and probably help. So if this is your throughput range, let us say input 1 becomes active here, input 2 becomes active here, and let us say maximum input 3 becomes active here. Okay. If I am using 1 as throughput manipulator, once it becomes active, I will have to use something else as throughput manipulator. Once 2 becomes active, I will have to use something else as throughput manipulator, right? If I use 3 as throughput manipulator, I can span the entire range without changing the throughput manipulator. Yes or no? Okay. If I use input 1 as my throughput manipulator, once it saturates, then I will have to change my throughput manipulator to somewhere else, right? People would like to have the same gas pedal. When you are driving a car, there is just one gas pedal that you have. So that's your throughput manipulator. Imagine a situation where you are changing the throughput manipulator. Of course, in a car it's a different situation because reaction time is of the order of human whatever, right? You can't. But in a plant, that's not really that big a deal. But preferably what you would like is that the throughput manipulator should be the same no matter what throughput I am operating at. If you are using 1 as throughput manipulator, input 1 as throughput manipulator, then once your throughput reaches whatever was the throughput here, then you can't jack it up. You will have to change some other set point, which then becomes a throughput manipulator to jack up your throughput, right? If you use on the other hand input 3 as your throughput manipulator, all throughputs below this are achievable using input 3 as your throughput manipulator, right? So you really don't need to shift it. Yes or no? So that simplifies my task. I have the same gas pedal for a large throughput range. Yes or no? So last input constraint to become active is a possible throughput manipulator. Advantage of that is you get the entire throughput range using the same gas pedal. Okay. If you don't do that, you will need to shift the throughput manipulator, which may be okay because plants have got a large response time of the order of hours, days, sometimes even months, right? So shifting a throughput manipulator is not really a big deal. Today I am using this to jack up throughput, tomorrow I may be using that to jack up the throughput. It's not really a big deal because the response time is much slower than human whatever comprehension, cognition, etc., etc. Alright, so if I use an input that becomes an active constraint, then what am I doing? You see, an input that becomes an active constraint should not be used to control anything, or it should be used to control only something that is non-critical. If I can use it for doing something that is critical, then I save a valve. Yes or no? I save a degree of freedom. Yes or no? Right. So if I use an input constraint that becomes active as the throughput manipulator, then not only am I eliminating the derating in that input, I am also using that same input for throughput manipulation. I have saved a valve, yes or no? That saved valve can help me get robust regulation, robust stabilization, yes or no? Agreed? Okay, so it saves a degree of freedom, a controlled degree of freedom, which helps process stabilization. Okay, and of course what I told you before, naturally transforms process variability away from the constraint, because once you set your throughput manipulator there, level controllers here will be this way and level controllers there will be that way, yes or no? Level controllers downstream will be in the direction of process flow, level controllers upstream will be opposite to the direction of process flow. That means upstream must supply the set flow, downstream must treat the set flow, yes or no? Yeah, okay, so that transforms variability away from the constraint, not into the constraint. Now you see, at any throughput there is a set of active constraints. Let us say you have increased the throughput by 30 or 40%, you find that your active constraint set is different. I can't keep doing this again and again and again for different active sets, right? So what I am now saying is synthesize the control system for maximum throughput operation. Why maximum throughput operation? Because that is the most difficult to stabilize. Why is it most difficult to stabilize? Because that has got the maximum number of active constraints. So if active constraints are tightly controlled using valves, fewer number of valves are left for inventory management, heat management, etc., 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 right? If I can stabilize my plant for this most difficult case, guaranteed when the throughput is reduced, I can run it, yes or no? So then what we are saying is synthesize control system for maximum throughput operation, where you got the maximum number of active constraints. Because you got the maximum number of active constraints, it is the most difficult to stabilize. If you can stabilize that, everything else is a cakewalk. Lower throughputs would be a cakewalk, because at lower throughputs additional input constraints will become inactive, yeah, and those can be used for getting better control, yes or no? That makes sense? Okay. So synthesize control system for maximum throughput operation because it is the most difficult to stabilize. Yeah, this is critical. Control. So now at maximum throughput, you know your active constraint set. Once you know your active constraint set, you control all active output constraints using close by manipulated variables that do not saturate or that never become active constraints. Yeah, okay, this makes sense. Choose an active input constraint as throughput manipulator to reduce throughput, and I would say choose an active input, choose an active constraint as throughput manipulator. I won't say input. Last active is a good candidate, but not necessarily. Okay, choose an active constraint as TPM. Okay, to reduce throughput. I am designing a control system for maximum throughput. I may be required to reduce throughput. Synthesize material and energy inventory control loops. What do you mean by material and energy inventory control loops? Level controllers, pressure controllers, reactor temperature controllers, right? Okay. Now dynamically test the robustness of synthesized control system. You see, in my enthusiasm to control all active constraints very tightly, I may have a level loop which may be unworkable. Yeah, that being the case, I may have a situation where the level inside a column, in the sump of a column may overflow or run dry for the smallest of disturbances. So then I get a non-robust level controller, or a non-robust pressure controller, or a non-robust temperature controller for that matter. Yeah, if that is happening, then what I need to do is, what that is saying is, I cannot control everything tightly, all the active constraints tightly, because it is creating a stabilization problem. I am not able to control my levels, pressures or temperatures well. So then what do I need to do? I need to back off, or rather relax my condition of tight control of all active constraints. Now the ones that are not economically important, I can say, well, those need not be controlled tightly, let me give up on that, get better level control, pressure control, temperature control, whatever was the cause of the problem, get those loops to work, and then give up on tight control of some things, some of the active constraints. Yeah, redo the exercise, test again. So I keep, it's an iterative process. I try the most difficult case, everything controlled tight, and then I put my level and pressure loops, see if it works. If it doesn't work, then I need to relax on some of the economically unimportant or least important active constraints, get my level controllers etc. to work right, get my inventory stabilization, energy stabilization right. Once the energy stabilization, inventory stabilization is done right, that is my best control system. Yeah, unconstrained degrees of freedom, you devise self-optimizing variables that sort of ensure that you are near optimal across the entire throughput range. Yeah, okay. So design procedure, degree of freedom analysis, you count valves, you count how many steady state degrees of freedom you've got, that's fundamental. The next question is, how do I play with them for optimal operation? So you do steady state economic optimization from low to maximum throughput, and this gives you an expanding constraint set. At low throughputs 3 constraints are active, then when your throughput goes higher, so many 4 constraints become active, 5, 6, 7. At maximum throughput, as many constraints are active as there are degrees of freedom. Yeah, so this gives you your expanding constraint set. Once you know your expanding constraint set, you know the worst, the most difficult case, maximum throughput, most number of active constraints, control all those, devise a control system for that case. Okay, and then as you are reducing throughput, degrees of freedom will become available. Use those degrees of freedom to control self-optimizing CVs, control variables, economically sound CVs. Yes or no? Does this make sense? So this is the procedure.